Hello, everyone. In this lesson, we will study engine block inspection analysis and preparation. We will cover engine block inspection analysis, measurement preparation, and practical operations. Through this lesson, I hope you can correctly list the inspection dimension table based on the engine block drawings, accurately configure the measurement probes and measurement angles, and complete the automatic inspection program setup. This will help develop scientific thinking and a sense of responsibility, fostering a rigorous attitude towards engineering problems and encouraging innovation. The engine block is a fundamental component of the car engine, and its machining quality directly affects engine performance. Therefore, high precision is required for its surface machining, and precise measurement techniques are typically needed to determine whether the block's dimensional accuracy is acceptable. Due to the function of the engine block, its shape is complex, with numerous oil holes, air holes, bolt holes, and other features, making the inspection more challenging. Let's review a real case. A car manufacturing plant overlooked the engine block inspection process, leading to a batch of blocks with minor defects. These defects were not detected initially, but over time, they caused a gradual decline in engine performance, eventually leading to several serious traffic accidents. After a thorough investigation, it was found that the inspection personnel failed to strictly follow the inspection standards and neglected to check some critical dimensions, resulting in this serious consequence. This case deeply reminds us that, as engineering professionals, every decision and action we take directly affects product quality and safety, as well as the life and property safety of consumers. Therefore, we must always maintain a high sense of responsibility and mission, approaching every inspection step with diligence and precision, never allowing any carelessness or negligence. Next, let's learn how to perform the automatic inspection of engine blocks. The first step is to analyze the part to be inspected, familiarize ourselves with the inspection content, and compile a list of the required dimensions. By examining the part drawing, we can see that it clearly specifies the reference points A, B, and C, which include one plane and two holes. Based on the principle of reference overlap, when establishing the coordinate system, priority should be given to using these reference points for alignment. After carefully reviewing the drawing, we organize the 10 measurement dimensions, associated features, nominal values, and tolerances into a table, as shown in the figure. As we can see, there are quite a few shape and position tolerances to evaluate, which are common evaluation items for complex parts. The second step is measurement preparation. The first task here is part clamping. Since the part has features that need to be inspected on all four sides in the top surface, in order to complete all required dimension inspections in a single clamping, it must be placed horizontally. For this case, the one-side, 2 pins clamping solution is recommended. The part's orientation relative to the measuring machine is shown in the diagram on the right. The clamping steps are as follows. 1. Use the fixture's bottom surface, the cylindrical short pin, and the anti-rotation pin to restrict the 6 degrees of freedom of the part by matching them with the bottom surface, bottom hole, and side surface of the workpiece. 2. Use the spiral pressing block to clamp the top surface of the part. 3. Complete the alignment and clamping of the part. Next is the probe configuration. Based on the distribution of features on both sides of the part and the required measurement dimensions, the workpiece's cylindrical through hole has a diameter of 30 mm, so a 40 mm probe length can meet the requirements. According to the drawing, the smallest hole diameter on the backside of the part is 04.5 mm, and a 02 mm probe is enough to meet this requirement. Considering the part's feature orientation, 5 measurement angles need to be added. A90B0, A90B180, A90B90, A90B90, and A90B60. Now, let's look at the actual operation. Create a new measurement program, name it student number 7, set the units to millimeters, and click OK to enter the program editing interface. The program parameters should follow the reference from task 3. Note that because the minimum hole diameter is 4 mm, the approach distance and retract distance should be adjusted to 1 mm. Click F10, go to Motion, find the BP retract distance R, and change it to 1 mm. Then click Apply and OK. Next, configure the probe file according to the hardware setup, including the probe holder, sensor, suction cup, and probe, and add the 5 side angles mentioned earlier. Follow the method in task 3 to calibrate the probe, and after completing the side calibration, confirm the calibration results. This process will not be demonstrated in detail here, as we can directly use the previously configured probe 007. Click OK. Please take some time to deeply reflect on the strategies for selecting the measuring probe configuration and measurement angles, and explain your choices along with the logic behind them. Building upon that, considering the case we discussed about the automotive manufacturing plant where a serious consequence occurred due to a lapse in inspection, think about the specific measures you would take to ensure the precision and high reliability of the inspection results. How would you ensure that each step reflects attention to detail and strict adherence to standards? This kind of self-reflection and strategy planning not only helps improve our professional skills, but also serves as a solemn commitment to engineering quality and social responsibility. In this lesson, we studied the automatic inspection technology for engine blocks, including key steps like inspection analysis, measurement preparation, and probe configuration. Through practical demonstrations and in-depth reflection, you have not only mastered the related skills but also gained a deep understanding of the importance of responsibility awareness. I hope that you will continue to promote this spirit in your future studies and work, contributing even more to our country's engineering and technology development. Finally, please reflect on this lesson and complete the following exercises to consolidate the knowledge you learned today and deepen your understanding. This lesson ends here. See you in the next class.